Alright, pause your thought for a second. I just have random things I have to tell you first. You ready for random? Here it is on the board. Raise your hand if you're not taking PSAT tomorrow. Lucky you. I'm there administering. The rest of us are taking it. But somebody's going to get a National Merit Scholarship. Yeah? Yeah. You can get it through getting a really good score on your PSAT. Okay? So, that's what I told you guys. I can't remember if I got like 20,000 or like 40,000. It was like either 5 or 10,000 a year. I don't remember. But get a good grade on your PSAT, you can get the money for college. But if you're not here tomorrow in my classroom, you're actually, if you're not taking PSAT, you're going to Mr. Smith's room, who's actually diagonal for me. So that's 1630. I have everything on my website that you guys will be doing. It's basically you're getting a head start on your unit review while the rest of us are slowly dying. Okay? So yeah, that's what you're doing, and then you're working on real life posters. If you need to finagle some of that planning, Unit 2 corrections, just kind of a work day for you guys. Okay? Thursday, tomorrow, no, 2 days from now, your Unit 2 corrections, test corrections, multiple choice are due, correct? Let's try to get that out so we're not having to do that any longer. If you have hydrogen peroxide to bring from home, bring some, because it's sometimes nice to actually trial run some of the hydrogen peroxide. We're doing the lab Thursday, BT dubs, we're not just bringing hydrogen peroxide. You are actually going to try to run some samples that you have at home versus the ones I have here. Friday, we'll be kind of reviewing the lab from Thursday, and it's kind of the same scheme. You know, we learn, and then we apply. It's hard to apply day 1 in the unit, right, because we don't know anything. We apply later in the unit, which is the last 2 days, Thursday, Friday. So what I'd like to make sure is for our lab Friday, which I'll tell you guys more about that later, but I'd like to see our lab notebooks prepped before we get to the lab so that we can kind of finish up early Friday and talk about the test on Monday. So we'll talk about that as we go. Monday is your Redox test. So for those of you who are still worried about Unit 2 and you're like, I don't know what grade I got, I'm still stressed about it, then hold off. Okay, I have like an algorithm that I'm running to see how I can optimize scores, but I can only optimize a 50 so high, right? It's not going to be curved to 100. We know that. So to give you a chance at redemption, I did try to curve the highest score up to 100, which is only like 7 points, and I'm not getting them over 100, right? So I can only curve it a little bit, which is about 7 points. So to help you guys out, if your Unit 3 score is better than your Unit 2 score, I will replace Unit 2 for you. I've never done that for any other AP class, BT dubs. Have not. But I want to make sure that you're studying for Monday test if that's what you wish to do. If your Unit 2 test was higher than Unit 3, I'm not going to replace it with a lower score. And then another note, in this quarter, which ends October the 30th-ish, we have another test coming in that period. Sorry, another test grade, which is actually a project, which is our mold day project on October 23rd, and we make t-shirts. And if you don't get 100 on that, shame on you. Okay? So I'll brief you guys on that as we get closer, but that's going to be your last test score in this quarter, so you should be fine, at least as long as you're giving me the credit, the effort that you guys have been doing so far. Other than that, I think we're good. Questions? Questions? Okay. So let's start back over here, and we're going to go over some homework stuff, okay? So when you're looking at A, first of all, reaction yay or nay? Okay, I see confused looks. Yay or nay? There's only 2 options here. Why yay? Margaret, what do you say?
Well, I said no because magnesium's more active than iron.
Just because she's got that activity series up here, right? You guys got it? What's your general activity series below? What's top? Group 1, then Group 2, then Group 3, like aluminum, and then, well, where on the transition metals? Okay, so it is left to right, but it's the first row of the transitions, and then sequentially second row of the transitions, but who's surprisingly low? Copper. Okay, so that's our one random fact about copper we need to know. So this is a no reaction. I'm just trying to get the border work. Going on to B. Will this one occur? Will B occur? Look at chromium. Look at lead. Will chromium replace lead? Yes. Okay. Well, I'm trying to get this fine marker. Sorry, it's okay. So this one's a no reaction, and that's because iron is less active than magnesium. So that's our clarification there. The solid is less active than the ion here. So is the solid more active than the ion? Yay or nay? Yes. So chromium will produce what? What charge? 3 plus, that's our charge of chromium that we constantly see. It's the highest oxidation state of chromium, supposedly. And then lead will form a lead solid through the single replacement process. So who's oxidized? Chromium. Remember, oxidation is the more activity series is regarding oxidation. So if you're really high in the activity series, you're likely to be oxidized because you're likely to lose electrons. So lead is a solid here. How many electrons were exchanged in chromium? 3. How many in lead? 2. Are the electrons balanced? No. So let's put some coefficients on to balance that. So we don't always have to have reactions. They are our saving grace, though, if you need to break it down. But you can also just tell overall, I have 3 electrons exchanged on one half reaction, 2 exchanged on the other. What is going to be my common multiple there? Our lowest common multiple? 6. Okay, so how do I get 3 to equal 6? Times 2, so I'm going to multiply the chromiums by 2. How do I get 2 electrons exchanged to be 6? Multiply by 3, so lead gets a 3, lead gets a 3. Okay, next one. Will iron, the solid, replace silver, the ion? Okay, are you guys looking at anything else? Then you're looking at periodic table, right? Not just at me? Like, looking in my eyes? I don't have any answers. All right, so iron is higher than silver, which is in the second run transition. So yes, iron will replace it forming a what? A 3 plus charge, and silver will form solid as it gets reduced. So total silver has an exchange of how many electrons? 1. Iron has 3. Why did I choose 3 by the way? Highest oxidation state, so you got to change it. It's not like, oh, I'll just lose 1 or 2, it's going to lose the whole shebang or get the whole shebang back. So what's our least common multiple? 3 electrons, so where do I put the 3's? In front of the silvers, okay. And that will balance out our charge and our atoms. Iron and magnesium, yay or nay? Yes, magnesium is very high, right? Super high on the activity series. Iron's going to then be going, magnesium's going to go to what here? 2 plus, and iron's going to go to solid. So we're just solid. So magnesium is oxidized or reduced? Oxidized by how many electrons? 2. Iron is reduced by 2 electrons, so charge balance 1, 1, 1, 1 coefficients. Zinc and tin? Will it happen, yay or nay? Yes. Okay, so zinc is higher than tin. Tin's way in the post-transition middle area anyhow. So zinc will replace, and zinc's going to form a 2, because that's our zinc's always charge, consistent charge, and tin will do what? Go to solid, and we have an overall change of 2 and 2, so we're good there. All right, so that's just referencing back to the activity series. On the next one, let's just do maybe 1 or 2 of these. Let's start with A. So we're adding magnesium to hydrochloric acid. So this is a combination of Unit 2 and Unit 3 where we have our reaction prediction, but then we're also recognizing the redox side of things as well. So you guys are adding magnesium to what? So HCl, producing what? Mg what? I heard 2 by like 2 people. Where's this 2 coming from? Charge of magnesium crisscross your charges. And so you should be looking at periodic table if you guys need to point out, do that now. And then as magnesium gets with chlorine, it crisscrosses charges. What else happens? Hydrogen gas is produced, okay, H2. So I can already tell you this is balanced, right? We're going to need to balance it just to get the atoms balanced. 2 in front of HCl. Okay, so now let's break it down to the NIE. What's left over? So magnesium, 0. Okay, what's left here when you get your NIE? Maybe tell me who's a spectator first. So there's an H plus there. Is there an H plus over here? No, so it's not a spectator. Who's the spectator? Chlorine. There's a chloride 1 minus charge. There's a chloride 1 minus charge. Those are going to be spectators. Can you guys start to see your NIE before separating everything out into ions a little bit? Sometimes you just need to take a minute and look. So chlorine's definitely a spectator. That leaves us with what here once the chlorine has been canceled? 2 H pluses yielding what here? Magnesium what? 2 plus, because that's the charge of magnesium. So the 2 chlorides here canceled with the 2 chlorides here. So those are gone, leaving us with what else over here? H2. Okay, so here's our NIE, right? And let's just analyze this orally. How many, who was oxidized? Magnesium by how many electrons? 2. So 0 to 2 plus. Who was reduced? Hydrogen ion. The hydrogen ion, each individual hydrogen ion was reduced by how many electrons? Each individual one went from a 1 plus oxidation state to a 0, right? So each one gained 1 electron, but overall we have how many? 2. So are the electrons balanced? Yes, because the magnesium was oxidized by 2 electrons, and the net total hydrogens were reduced by 2 electrons. You guys okay? Okay. Looking down here, these should be quick actually on this one. Turn and talk to the person next to you about 1, 2, and 3, who would be most likely to, or who most expected to rapidly react with HCl.
This one?
All right, what we got for 1? 1? Who is it? I hear both, but I heard aluminum more. Aluminum's in group 3, so it's more active than the first row of the transitions. Okay, and then next, why nickel? Farther left in the first row of the transitions, just by hair. And then, for sure, magnesium, right, because it's in a group 2. Alright, so on the setup that you guys have, my numbers are all messed up because the smartboard doesn't like numbering. Cancel out 2 and 3, so we're not going to learn non-oxidizing acids and oxidizing acids. If you want to look that up on your own, there's stuff on my website. It just gives you a little more detail about why some acids react and why some acids don't react. But it's not included in our level of depth anymore. There used to be a whole lot more content in AP Chem. First year I taught it, it was like the devil. It was so much information. So you'll notice some remnants of those, some structures that are left that I haven't taken out, just in case I have time to teach extra stuff. Okay, but by the way, we don't, because you guys know that we have 2 semesters of college chemistry to learn in less than 2 semesters. Because we get out. We test a month early, May the 6th or something like that. So I want to start the calendar in like early August so we can get out by Memorial Day, but you know, I'm one person to start this movement. Okay, so turn and talk to the person next to you about 4 and 5, and let's figure out if we can use our terminology correctly if we were to like explain something like this on the pre-response.
Alright, so since aluminum is more active than iron, it is more likely to be
Try to use terminology.
Therefore, aluminum oxides. Yeah. And then what's the other one? Cross reaction with boric acid. Alright. By honey copper. Non-reactive with boric acid. Because you turn on the place, which is hydrogen, because it's less active. So then nice.
All right, and come back to me. Please, little area. Tell me what you got. What you said for 3.
I said that aluminum's activities, aluminum is higher on the activity series, which means it will oxidize more.
So I'm gonna modify and just put more easily oxidized. Okay, so I know it says active, right? So we need to elaborate on that in terms of oxidation reduction terminology. So aluminum is more likely to give up electrons, meaning easily oxidized, right? Due to low, and I'm going to add just a little bit more to this to foreshadow where this is going, due to lower electronegativity and ionization energy values, which are something we'll talk about more in the spring, but the idea does spring from the trends of the periodic table, than iron. So who between the two, iron and aluminum, would be the better oxidizing agent? Remember how the agents flip? Okay, so iron is a better oxidizing agent, but aluminum is a better reducing agent, but aluminum itself is going to be oxidized. Okay. Oxidation reduction, explain why copper will not react with hydrochloric acid. This might be a little challenging, but who's got me here? Give me a thought. Copper's lower than...
Copper is really stable. It doesn't like giving up its electrons.
Okay, so we can't personify them. Like, it doesn't like to give up electrons. So I heard like a combination of that though. Not likely to give up electrons to whom? Okay, so we have copper basically, right? And HCl. Copper can only do one thing, and what is it? Oxidation, right? It can only give up electrons. It can't take on, have you ever seen copper with a negative charge? Never, right? So it can only oxidize. But what can these guys do? What can H plus do? It can reduce, right? So H plus can be going to H2 to gain 2 electrons. What can chlorine do? So H technically can go from H plus to H2. What can chlorine potentially do? Or chloride potentially do? Cl2. Okay, so what's happening for this one? So this one's rig. Oops. And this one is oxidation, right? -2, 0. Okay, and what does copper have to do? Oxidize, right? So copper is basically competing with the other one that needs to oxidize. So what two should we be focusing on? Copper and chlorine. So truly the idea is that between the two, one of them is going to be the stronger or have more likelihood to oxidize. So we have to compare them, but we don't have any kind of chart to compare them necessarily because chlorine's kind of off in its own little world. It's not a metal that we would consider from the activity series. So that's something called the reduction potential list, which we'll talk about more when we get to electrochemistry, which is like January. But so this idea is that one of them, that's the free element, is not strong enough to oxidize in the presence of chlorine. So copper is not strong enough to oxidize itself in the presence of chlorine. That's kind of how we would state that. Or it's not as likely to give up electrons as chlorine would be. Okay, so this number 5 and 6 was something I actually wanted to talk about yesterday, but we were predicting and doing stoic at the same time, so I tried to hold off on this. A lot of you guys were like, this isn't a redox reaction when you were going through some of your reaction predictions, and you should have noticed that because the ones where we were keeping the same oxidation state, nothing oxidized or reduced because we kept the same oxidation state, and then like hydrogen was always a +1, oxygen was always a -2. So what happens is when we have the acidic anhydrides and the basic anhydrides, the synthesis part where we made the anhydride is redox, but the addition of water is not redox. So for example, the synthesis of, let's do it, give me a non-metal oxide to make, say again, Cl2O? So the synthesis of Cl2O, okay, so that's going to be what plus what? Say again? Chlorine plus oxygen. Okay, synthesis of a non-metal is going to be 2 non-metals coming together as a singular state. So technically, I mean, this is what we're making. We'd have to balance it out. So this right here is the synthesis of the non-metal oxide, which is the anhydride, correct? Is this redox? Yea or nay? Yeah, like free metal. I mean, a free element, and then some sort of differences in oxidation state. This is redox. But when we now do that anhydride, making it hydrated, we're going to take this guy, add it to water, and the rule of thumb was you had to keep chlorine's oxidation state the same, right? And this was one of the ones on the prediction. So what's this product? H. Say again? I heard HClO. Let's just double check this. What's the oxidation state of chlorine here? So this is a -2, so this is a +1. Okay, what's the oxidation state of fluorine here? So this is -2, this is +1, so this is also +1. So this is correct. So overall, though, we went from oxygen being -2, -2, -2, hydrogen with a +1, +1, +1. Chlorines all stay the same. So is this redox? Does this have any oxidation state changes? No. Okay. So the synthesis of the anhydride is redox, but the hydration of that anhydride to make an acid is just a reaction prediction that you should be comfortable with, knowing that the oxidation state is something to be concerned about, but we're not actually changing oxidation states. Does that make sense? It's just some clarification on why we were doing that yesterday. Not redox. Can I move on from here? Did this actually make sense? Yes, yes. Say again? So, acidic anhydrides are non-metal oxides when added to water form an acid. Acidic anhydrides are non-metal oxides when added to water form an acid with the same oxidation state of the non-metal. I'll add that with these. Okay, I hope I can remember what I said. Acidic anhydrides are non-metal oxides when added to water form an acid with the same oxidation state of the non-metal. Definition. Okay, so that's why we kept our chlorine's oxidation state the same. And same applies for the basic anhydrides, just change the word basic and then base. Yeah. Oh, gotcha. So the actual acidic anhydride is this guy. So we synthesized the acidic anhydride first in a redox style reaction, and then we took the acidic anhydride, hydrated it with water, made acid. And that non-metal has the same oxidation state. All right, so good terminology, guys. Good. Let's do a little bit of combustion here. Just simply define combustion. Going down here. Trying to talk first, maybe, because you guys are like, oh, I'm not sure. You're just mumbling. Alright, and then please write the reactions for 8. All those, write those reactions. You might need some more space. I don't know if you saw how nice that was. I gave you the structure in the name, or the formula and the name. I mean, paraffin wax, guys. You shouldn't have. You shouldn't have used paraffin wax. It's just like candle wax. They both go. They both go. And this is my disclaimer. Balance it like you would balance it in honors chem, because there's sometimes the idea of oxidation reduction can complicate your process. Just balance it like normal. It should work out.
See 21, page 44. So yeah.
Once you get done with this, who's already done with this? Okay, go to the quiz. Someone asked me for extra multiple choice practice. I have delivered. Okay, start on the quiz, which on the other side is a low stakes thing. You're just doing it with me, but start without me for the moment. Make sure I'm good there. And this, oh, I didn't get them double. That's the worst. Hold on. Should guys work on your quiz for a second? I'm sorry, there was something. On number 7, do not regard the answer choices. Look at number 7 for me. The answer choices A, B, C, D, and E. Scratch those out. Choose one of the Roman numerals 1 through 5. It's one of those answers. So it's not the actual A, B, C, D answers. It's one of the Roman numerals 1 through 5. whenever you're done, grab your laptop for me. We're going to check this in a second. We're going to check over to Redox storage. And you guys are starting pre-lab. Grab your laptops. Let's look at join shifts here. Alright, a couple more people go grab their laptops, please. Join shifts here. And just get that thing logged on. You're just supposed to try yourself. Don't ask around. So you're doing yourself self-reflection. You're asking people for yourself. If you're wrong, you just have to own it and make up for it on the test. Just quick. The rest of you grab your laptop, please. All right, we are officially calling time on that. Let's try to make sure we're good to go here. I know number 6 is probably the hardest one. Can we agree? 6? Or did you feel good with that one? I guess you'll maybe know after you get the answer. Okay. All right, so answer 1. Shout them out. Let's go. A, good. So you're looking and just assigning oxidation states. And we all know that permanganate does not have a -2 charge, right? It's just the example that was there. Permanganate has a what charge? -1, okay. Number 2. B, okay, simply assigning oxidation states again. 3. Say again? D as in dog, okay. So you just had to go through and assign oxidation states, but you should be getting quick at that. 4. E as in elephant? E as in elephant, right. So when you're going through in a quick fashion, immediately, did you guys notice A and B and C were all wrong? Yeah. Think that was wrong? Okay. So A, B, and C are all wrong because hydrogen is wet. Hydrogen is wet in general over the course of this reaction. It doesn't oxidize or reduce, so you cannot be including it as an oxidizing agent or reducing agent or anything because it's not doing any of that. But then as you went down to D and E, as you kind of qualified by writing oxidation states, you should be able to get E. 5. Okay, so I heard C, and so if you see A, single replacement, that magnesium automatically changes oxidation state, right? And then you see B, oxygen, free element to a compound, automatically changes oxidation state. Sodium, automatically changes oxidation state in B. And chlorine diatomic automatically changes oxidation state. So I didn't even assign oxidation states to anything, except for the C one, just to verify I was right. Like, it wasn't a trick question. But it is a synthesis one that takes into account no changes in oxidation state. Let's get 6 for a second. What did you guys get for 7? 3? Okay, good. Now let's go back to 6. Shout it out. See all these questionable, you're like, I'm not sure. All right. Here's your letters A. I want to see, look at your sign language for you. A, B, C, D, or E. Throw them up. Please participate in my survey. A, B, C, D, or E. I need to see your hands. This is a real quiz, guys. All right, so I got a couple of C's. Okay, hands down, a couple of C's. So answer is C, and the reason why. Here's how when I read this, here's how I processed this in less than a minute. Okay. Blah 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 blah. Metal D was placed in solution. Okay, so metal D was placed in solution. So that's our solid, right? And it's reacting with A and B. So it says it actually reacted, or reactions were observed in A and B. So that means D is more active than who? A 2 plus and B 2 plus, or whatever it was listed as, yeah. So that means it's more active than A and B collectively. So here's my activity series. Boom, boom, boom. A, B, C, and D are going to go here. So D is up high. A and B are down here. They're down low someplace. A and B are kind of in these two regions. Because in the next statement, I didn't, sorry, I didn't tell you this yet. It says metal D was placed in each of the solutions. That means A, B, and C. So if it reacted with A and B, it means it's more active than A and B. What does that tell you about C, though? C is higher, so C is more active than D. So C is at the top. D is second. A and B are collectively down here. So automatically, looking at your answer choices, where can you eliminate them? A, B, D, and E. You didn't have to read the rest of the question. But just to clarify, metal C reacted with a solution containing D 2 plus ions, which makes sense. And this says it wasn't tested with the rest, it doesn't give you conclusive data. And then list the metals in increasing, or sorry, B did not react with any of the solutions. I missed that one. If B didn't react with any solutions, where is it listed here? The bottom, because it's the least active, so then A has to be here. So this is your order, like conclusively, but you could have answered that question without actually doing the whole thing. Okay, so keep that. That's probably good practice, and I'll throw up some more. I think I have a soccer tip sometime. All right, let's check over stoichiometry first. Okay, so let's do 4 and 5, and then we're going to break out into our pre-lab groups. Okay, so 4 and 5. Who got 4 right according to the answer key? I see no one. Thank you, Gigi. Thank you for teamwork. Okay, put 3 people. Okay. Oops, let me undo this. So you had your solutions of sodium chlorate and sodium bisulfite, and as you were reading, they told you the prediction. Expect that most of the time, guys, you will have the prediction somehow given to you, or it'll be an obvious prediction, like chlorine to chloride, or permanganate to Mn2 plus, because we've done that one like, I don't know, 5,000 times. So there's going to be some very familiar ones to you. Please don't be freaked out by reaction prediction. All right, so as you're going here, you had to do your what first? Balancing reactions, half reactions, right? Okay, so in terms of balancing your half reactions, I looked ahead first just to see who was oxidizing, who was reducing, so I just noted that for myself. But overall, you have your bisulfite going to sulfate, and then your chlorate going to chlorine, balancing with an acid, so hydrogen or oxygens with water, hydrogens with H+. Electrons, there was 2 electrons on one side, 6 on the other side, so you had to balance out first by multiplying your 3 coefficient across the board to get 6 electrons balanced. As you pull everything down, it should be 1 chlorate ion. Make sure you're putting your charges, or your charge balance is totally messed up. 3 bisulfite ions yields 3 sulfate ions, plus 3 H pluses, plus 1 chlorine ion. So thumbs up if you got your equation. Or if not, you were writing this thing down. In terms of balancing, where do we struggle here? Yeah. On this one up here. So as you added your sulfurs were balanced, you had your 3 oxygens here, you had 4 here, so I had to add 1 water over here. So then 2 H pluses, and that says, no, sorry, 3, so 1, 2, 3. 3 H pluses here. So overall, a 2 minus and a 3 plus gives me a 1 plus net charge over here. And then this is a 1 minus net charge collectively here. So I need to get a 1 plus down to 1 minus by adding 2 electrons to this side. And then that's then going to be multiplied out to get 6 electrons. So other than maybe a brain fart, I don't think this right here, given the predictions, you should have had no problem with this observer. Just saying. All right, so then as you take your stoichiometry into account, given the 25 milliliters of 0.4 molar sodium bisulfite, start with that information, get to moles or millimoles, whichever you prefer at this point. And when you get to your moles, by multiplying, basically molarity times volume will always give you moles. That's our kind of go-to thought. You're then going to go straight from moles to mole ratio. So in this case, this is a 1-to-1 between sodium bisulfite. So I actually just scratched my spectator out there just to indicate I have bisulfite and bisulfite. But between the chlorate and the bisulfite was a 1-to-3. And then sequentially moving on to molarity, I was in millimoles of chlorate, so then went with the molarity given as 0.1. So then that was 0.1, 1 milliliter. I kept everything in millis and just answered my question in milliliters. You could have done liters just as well. In terms of sig figs, 3 sig figs all the way, 3 sig figs at the end here. So mental math wise, 25 divided by 3, approximately 8. Okay, is that right? Oh, I missed something. Sorry. Well, okay. So 25. How would you guys do this? Can you do 40% of 25? That's 10, right? So 0.4 is 40% times 25 is 10. Divided by 3 is 3.33. And then when you divide, so we have 3.33, and you divide by 1/10, which is 1/10. You end up multiplying the 10 on top, which is why you get 33. Mental math. Okay. And then the next one, this is very similar to how our lab is going to be designed. We have a lab on Thursday with potassium permanganate and hydrogen peroxide, which is why I had the random facts. Please bring hydrogen peroxide if you wish on the board earlier. So it's titrated in the presence of acids, or acid, or it's acidified with sulfuric acid. So that's the fact that tells you it's acidified. Do not use that at all as a reactant because the sulfate is a spectator ion. Just the H+ is available for balancing purposes. So you had your hydrogen peroxide and your permanganate. The spectator ion would be K+ here. And so and I'm going to show you the permanganate first just to give you a heads up on how you can get back to hydrogen peroxide. The permanganate is a strong oxidizing agent. So it's going to be going from Mn O4 to manganese 2+ all the time. And so if we ever see that, that's generally your prediction. If you have to balance your oxygens, you add your waters, add your hydrogens, 5 electrons on that side, we're good here. So this one right here, this half reaction, is this oxidized or reduced? Look at where the reactions are, or the electrons are. The electrons are in the reactants. If electrons are in the reactants, they're being gained. So it's, ooh, that was like pulling teeth, guys. Are you just sleepy? Okay, are you okay? Should I even continue? Are you absorbing this information? Okay, I don't want to go over homework if you're not absorbing it because it's useless of your time and my time. But I think you should know this. So here's how you approach this if you don't have any idea what the other reactant is doing. Go with the one you know. So that's our permanganate going to permanganate ion. Blah, 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 blah. We see this one's reduced just by the placement of the electrons. So the other one has to be what? Oxidized. So hydrogen peroxide comes to make 2 products. And this was what we wrote on the board yesterday. Hydrogen peroxide can make either oxygen or water. So your job is to figure out which of these products is the oxidized version of that. And so I will tell you it's oxygen because you're going from a -1 oxidation state to a 0. So what happened to its electrons? Remember the peroxide is a -1, right? It lost electrons, so that's what we're seeing over here too as we balance this out. So this took a second, but you add your oxygens were balanced, so then you added 2 H+ to make it atom balance with H. And then net charge over here was 2+, so I added 2 electrons to equal out a neutral charge over here. Noticing now that I have 2 electrons and 5 electrons, so then to balance that out, you need a 2 and a 5 to multiply out across as coefficients. Took a second, but I pulled everything down first and then canceled and simplified as I went. I think that's sometimes easier because I can get it all in one place. You guys can do whatever you please. But in the end, you should have 5 hydrogen peroxides, 2 permanganate ions, yields 5 oxygens, 2 Mn2+, and 8 waters. Yeah.
Where did your 6H+ go?
Where did my 6H+ go?
You took 16H+ down to 6H+ to 3H+.
On my scan versions, I don't have on. This was scanned however long ago, but on my written version, I've fixed that since then. Thank you. So it's 6H+ right there. All right. So here's our BCE. We have our relationship between hydrogen peroxide and permanganate, which is the most important point. Its ratio is 2 to 5. And given that you use 10 grams of hydrogen peroxide, 17.6 milliliters of 0.2 molar potassium permanganate, you have to start with your titrant, which is your known. So again, we're taking molarity times liters or molarity times milliliters. And so 17.6 times the molarity of potassium permanganate, which in itself is a 1-to-1, so I just went straight for the ion here. And then including now getting to hydrogen peroxide, you'll use your ratio of 5-to-2 from the reaction you guys just established. And then the question here was to get to milligrams or grams. Was it milligrams or grams? Or just say mass? Just say grams. Sorry, okay, I would have to go farther. But when we get to mass in general, we get from our moles of hydrogen peroxide to grams of hydrogen peroxide in 1 mole. I just use milligrams in this case. But regardless, we have about 300 milligrams or 0.3 grams, 0.299 grams. I saw a couple of you guys actually get this part. Questions so far? Okay. And then lastly, taking like we did yesterday, once you get the final mass, and then it says find the mass percent in the original sample. The original sample you had was 10 grams. In that original sample, it's obviously not pure hydrogen peroxide, because if not, all of those hydrogen peroxide grams would have reacted. So we then take our grams that reacted, which is 0.299 grams, divided by our original sample, 10 grams to give us about 3% hydrogen peroxide, or 2.99% hydrogen peroxide. Expect that you will see something like this in the test, where you take grams to a percent of an original sample. Okay? Yeah.
On one of these examples that we did yesterday, it said like we put tin in acid, and then like we did a before reaction where we made it SN2+, and we used that in the project.
It actually doesn't affect, so this one doesn't come out like that. It didn't affect our math at all there. It was just recognizing that the tin-2 came from tin solid, which is in a 1-to-1 ratio with itself. If it were ever a coefficient difference, we would have to implement that into the stoichiometry process. But usually it won't, because a lot of times our metals are just, they're forming their highest oxidation state, but their coefficients are still 1-to-1. Yeah. Say again?
Which type of reaction do you have to make?
Add electrons? Like in the half reactions?
Okay, is that the
Just half reactions, you should have to do that, because that's just going to ensure your charge is balanced across the board. Alright, so I'll answer more stoichiometry problems. I actually had someone ask me about just getting some more, so I printed out, these were some old FRQs that College Board put out, and they have some good samples, so I figured if I just left these in your hands, you could decide to either throw it away or keep it for study evidence or whatnot. So here's a couple like that. And then extras pass all the way over here, okay? So just put SC on the top, so if you want to do anything regarding study evidence there, you can, okay? Alright, everyone's on my website, yes? Get to my website, and then let's talk from here. Okay, here it is. So, because we're not going to do this lab till Thursday, I'm going to have you try to complete your pre-labbing class today. So let's talk as we go. You're on my website. Go to the link under tonight's homework, which says, what does it say, Miriam? The link under my homework was this. So the AP homework for me. There it is. Prepare redox titration lab, okay? So in the packet I gave you, you had a 4x4, like a 4 lab to 1 sheet. Can you guys pull that up for me? Packet I gave you day 1. I call it a packet. It was a bunch of loose papers that you guys decided to potentially staple together. So I'm going to show you where that is here. And, oh, JT, did you give stuff to Emily? Did you give Emily's slides to her? That confused look on your face, you're like, I don't know anything. So I know you're multitasking, pulling out papers and looking up here. Alright, so in the 4x4 sheet, I have that actually up on the board or in a link form for you as well, but I wanted to let you know you had a 4x4 sheet that has everything on it if you'd like to go ahead and think about scribbling on this, highlighting things that you need to do. But our main goal is to, and this is your kind of your purpose, right? The main goal is to take hydrogen peroxide sample and determine the mass percent of a commercial solution, which would, like we would buy off the store shelf, or from your bathroom, which if it's been sitting in your bathroom for like 5 to 10 years, it's hopefully decayed or decomposed to the point where it's no longer what it originally said from the store label. Okay, so the standardized solution of potassium permanganate. So I have standardized the solution, and I have one version for you to use, and it's 0.02 molar potassium permanganate, and that's our standard solution. You're going to then do your data analysis and compare it to the published percentage on the store bought label, and then we'll do percent error from there to see what in the end has occurred to that hydrogen peroxide in the bottle. It's a very simple process, but you need to do the pre-lab together first, just so I'm aware that you know what you're talking about, so your lab procedure is spot on. So some limitations, though, for your lab procedure. There's a ton of stuff on the list. Do not just copy the whole list. Use specifically what you need to use. And I give you some character or some limits. You cannot have more than 10 molar sulfuric acid because it's super concentrated. You are going to have to do 2 trials at least this time. The last time we kind of ran out of time for trials, but we know we're real chemists here. Make sure that you get at least 2 trials in. So I would split it 5 to 5. We have to acidify our solution, or the reaction will happen so slow we will never see a change, or it would actually look as if it was happening in base because it wasn't acidified enough. What does permanganate make in base? MnO2, which is a what color? No, Mn2 plus is pink. MnO2 solid is black, brown, flaky, yucky looking. Okay. And then sodium hydroxide, you need to include that at the end, but sodium hydroxide you should be using that to clean out your burette at the end because potassium permanganate stains. Okay, so it's purple, it stains. Facts about the density of different solutions. Supposedly 3%, 6% are these densities, and then potassium permanganate, the molarity that I have here, is that molarity, is that density. What is the value of density to us in the lab? Think about in the lab, we're doing a titration. What kind of data are we collecting? We're doing a titration. What kind of data are we collecting? Loud and proud, people. I can't do this one. Thank you. We are determining the volume of something. Okay, so volume, if I need to find mass percent, I have to eventually get to what? Grams, right? So how do I get from volume to grams? Density. That is the only valuable character or a valuable trait that density has. It's a connection between mass and volume of something. And then in terms of describing our best design of your procedure, follow those restrictions there. And then I added one thing here. You need to be drawing solutions before and after the equivalence point to get used to those particulate diagrams a little bit more, especially if you see something like that again on your test. Okay, so those are like just the basic review. You guys can see the lab sheet that I actually have provided you here. I've updated one link though, so it's much easier to access that here. And then this is just me talking more. I have some highlights there that might give you some tips on like error analysis. Okay, so choose one person right now, flame them with your eyes, flame them. Okay, let's knock out some of that pre-lab together now. Okay, I'll put you guys back in 15. We have pre-lab time for 15. Make a shared Google document, or one person can type, whatever. I was going to try to do 30 minutes, but there we go. Feel free to be first, but you should read that number first. So work collectively and fill out the units. I need one group of 3 years, 25 people. So the pre-lab is under the student lab sheet. The pre-lab is under the student lab sheet. There's some simulations and reading you're doing first.